All right, today's Monday, May 11th, and one of our last weeks of assignments. And we're going to go over a variety of problems. We'll do 2 problems today that have a whole bunch of things added to them, and then we will do 2 problems on Wednesday. So this is a problem that was something we did, but it has now gotten longer because I added to it to make sure we cover as many topics as possible. These problems will be due on Friday, May 15th at 11 p.m. So bone mineral density is a measure of bone strength. It is defined as the ratio of bone mass to the cross-sectional area of the bone that is scanned. And it is expressed in units of grams per square centimeter. Recent studies suggest that the peak of bone mass density in women is achieved between the ages of 15 and 40, and bone mass density declines after 45. Decreased bone mass density is associated with increased risk of bone fracture. In a recent study, the impact of calcium supplements on bone mass development was examined. A simple random sample of 62 women between the ages of 41 and 45. The women were placed in 2 groups based on whether or not they took calcium supplements. They said, simple random sample, that's important. And we had 62 women, ages 41 to 45. The women were placed in 2 groups based on whether or not they took calcium supplements. All right, so we notice we have 31 women per each group. And anytime I see something that's the same size, I wonder if they're paired. In this case, they are not, and I know they're not. And the reason I know they're not is because there's no meaningful association on the way the women were assigned to be together. So there has to be some sort of association. Has to be some sort of relationship there. And in this case, there is no relationship. So consequently, we have no reason to believe that this is going to be a paired test of any sort. It says construct a 94% confidence interval for the difference in BMD between those who took supplements and those who didn't. So the next question is, well, they want me to do a confidence interval. That's obvious because they say 94% interval. And generally speaking, if they want you to run an interval, they're going to tell you to do so. They want this to be for the difference, which is good. It means we don't have to worry about doing a one-tailed test. And for the AP exam, I wouldn't worry about that when it comes to confidence intervals. And then the question is this going to be proportion or means? Well, since they gave me means and they gave me the standard deviation, and I need both of those things in order to run something for means, or I need raw data. Since they didn't give me raw data, but they did give me means and standard deviation, I know this is going to be some sort of test for means. So the null hypothesis, which is not necessary to write for a confidence interval, would be that the 2 are equal. The alternative, because all confidence intervals are 2 tails, in this case our tails would look something like this. 0.94 in between with 0.03 in each tail. All right, so we always do have to define, regardless whether we're running a hypothesis test or confidence interval, we need to define our variables. So mu are the ones we're interested in, which in this case, mu1 equals the true population mean bone mass density for sedentary women, and mu2 is the true population mean bone mass density for women who actually walk. So I'll write down my formula, which will be on the formula chart, or at least the one that I provide you, or on the inferences cheat sheet. And degrees of freedom. Now, where did that come from? Because there's a very complicated formula, but you don't have to know it and you don't have to use it. That comes from actually running the test. All right, so we will use that, and it's a really important number for confidence intervals because we will use that to calculate our T-star. All right, our T-star will come from that degrees of freedom. So let's go ahead and run this test. All right, stat test. And this is a 2-sample T interval. And My sedentary women had a bone mass of 1.151, with a standard deviation of 0.068, and the sample size was 31. For those who exercised, it was 1.209, or those who walked. That standard deviation was 0.067. My sample size was again 31, and we wanted a confidence level of 0.94. So when I calculated this, I got the degrees of freedom of 59.98 7, which is what I wrote down here, and we'll come back to that in a moment. Now, I guess I should have noted this, but I went ahead and plugged in. That's my sedentary women bone mass. This is those who walked. This I'm about to calculate. This is the standard deviation for sedentary, standard deviation for those who walked, sample size, and this is the interval that I calculated, which came straight off the calculator. Now, the reason the degrees of freedom is important because I need to calculate that T-star, so let's go back and calculate that. So second bars, inverse T. My area is going to be parenthesis 1 minus 0.94 divided by 2. The degrees of freedom is approximately 59.987. And I get a 1.917 for my T-star. All right, so that's the computational part. And from this, we are 94% confident that the true population difference in means in bone mass density of sedentary women and those who are walkers lies within the interval negative 0.0909 and negative 0.0251. A lot of times, if you want to make it easy on yourself, you can say sedentary minus walkers, and just put that in there, and that lets them know the order that you went in. And usually I do that. All right, based on the results, can it be concluded that calcium supplements resulted in higher BMD levels? All right, so 0 does not lie within the interval, and the interval is negative, which indicates that the difference is statistically significant, with the BMD of sedentary women being less than that of walkers. All right. While the results are statistically significant, this was an observational study and not an experiment. Why? Because treatments were not assigned. I probably should have said that. I probably should have made the comment. This was an observational study and not an experiment because treatments were not assigned. Thus, it would be incorrect to assume causation, and it would be incorrect to determine that changing the sedentary women to walkers would increase their BMD. That second part was really, really important because that was the actual question that they actually asked. So the last thing, and the reason why the observational study can't be concluded, it's possible there are other factors such as weight, diet, or general health that may be negatively impacted the BMD of sedentary women. Now, we don't know that. That's just a supposition, nor was that statement required. All right. I'm going to go ahead and put a pause on that so we can talk about that part of this problem before we move on. All right. So when doing questions, it was pointed out that I had left off the conditions for part A. I would have lost a point right there. And it's a point that I shouldn't have lost. I should have actually done my conditions. So what were my conditions? Well, first off, condition 1 should have been 2 independent random samples of size 31, and you don't have to give the size, of size 31, and that was given. The next thing needs to be the N is less than 10% of the population. So N less than 0.10 of the pop. Well, both samples are size 31, so I can combine them, go 31.10 equals 310, and it's reasonable to assume more than 310 women walkers and those that don't walk. Sorry that I'm all jammed up against the corner, but I goofed up and didn't include conditions, which was really important. And the next thing, n equals 31, which is greater than or equal to 30. So we are normal. I'm going to abbreviate, don't do it on the test, by CLT. Normal by CLT, or central limit theorem. The populations appear normal enough. Appear normal enough. All right, so my conditions should have been 2 independent random samples, and I needed to make sure I stressed the word independent. I need to include the word random. And that was given. It told us that. And then it needed to check for the dependency, because we're sampling without replacement. So n is less than 10% of the population. So we know that there's more than 310 women who walk. We also know there's more than 310 women who don't walk. The next thing is our sample size, or normality. And our sample size was 31, which is larger than 30. So in this case, we are normal by central limit theorem. Interested as to whether or not the supplements are more effective than walking in slowing the decline in BMD, scientists wish to design a study to compare the effects of walking on BMD as compared to the supplements. 300 randomly selected women aged 30 to 60 are available to participate in the study. The women are not known to have any pre-existing conditions and are in good health for their ages. Design a completely randomized design with a control group for the study. Well, first, I would begin by measuring the women's BMD. Then I place the names of all the women, all 300 women, in a hat and mix thoroughly. I would draw names without replacement. The first 100 names drawn would, and by the way, please don't forget to address whether or not replacement is or is not allowed. The first 100 names drawn will be placed in the group of walkers. The next 100 names drawn will receive the supplements, and the remaining would be assigned to the control group. It doesn't matter which order you choose, just make sure you do so. If you're working with objects, you're going to have to number the objects and then place the numbers in a hat, and then at that point, you're going to choose the object that corresponds to the number drawn. But since we're dealing with people, it's just easy to use their names. At the end of an appropriate time frame, I'd measure the BMD of the women and compare to determine which treatment was best at retarding BMD loss. Really important that you talk about the comparison at the end. All right. So we measured it at the beginning, and then we decided to compare at the end to see which treatment was more effective. What was the purpose of the control group? Well, the purpose of the control group is to let scientists know whether the observed changes are due to the treatments that were assigned or due to some outside variable. It's always best if you can give some sort of explanation and context. So basically, the first part was the definition. The next part is the explanation as to why that might be. You are not scientists. You're not doctors. You don't have to be perfect. Just come up with something that might make sense. For example, BMD is known to progress as women age. Well, I know that because they told me that earlier. They said after 45, they have loss. And the control group would provide a baseline of BMD loss for the women so that the scientists would know if the loss had been retarded for those in the treatment groups relative to those in the control group. All right, so that's the purpose of the control group, is to provide a baseline because there's some variables that we have not had an opportunity to control for. I'm going to go ahead and pause right here for just a moment. So one scientist suggested that blocking might be helpful for the study. On what variable would you block and why? Well, they didn't tell us a whole lot of things, but they did tell us that age was a factor. And because age is a factor in this, then I'm going to block by age, because all the women are, oh, and they did tell me that they were in good health. So since all the women have similar health, I would block on age because I believe age will have a large impact on the results of the study. How do you choose what you block on? You always block on the variable that is not that has the greatest impact, that's not the response variable. So we're not going to block on BMD, but we'd either block on something like health, or in this case, age. We're not blocking on health because everyone is in good health. If you had different health levels, you might want to block on health at that point. But here, we block on age because we know that it has an impact, and they told us it did. I believe this because we know that BMD progression tends to occur after age 45. Or it should be BMD loss progression occurs after 45. I would separate the women in two blocks, those under 45 and those over age 45. Great. Design a study that includes a control group and blocking, being certain to list the treatments and the response variable. And I didn't do those last two parts. I didn't. So, and I should have done that. I would begin by measuring the BMD of all women in the study. Because all of the women are in good health, I'd block on age because we know that BMD progression tends to occur after age 45. And then I would separate the women in the two blocks, those under 45 and those over 45. Since I'd already included that in part E, I did not need to include that in part F. But if there had been no part E, I would have needed to include it here. Within each treatment group, I would randomly assign treatments. I would do this by placing the names of the women in a hat that were under 45 and thoroughly mixing them. I would draw the names without replacement. Again, I address replacement. The first 1/3 of the names would be assigned to walking. The second 1/3 of the names would receive the supplements, and the remaining 1/3 would act as a control group and would receive neither of the treatments. I would repeat this assignment process for those over the age of 45. So basically, the very first thing I did was I blocked based on their age. So you block first, then I assign treatments, and treatments need to be randomly assigned, and you must say what the randomization process is. I said names in a hat, mix, and draw, but you must state that. And I explained it for one group, and then for the other group, I said, hey, I would repeat this assignment process for those over age 45. That way I didn't have to write the same thing down twice. At the end of the appropriate period, I would measure the BMD of all of the women and compare to determine which treatment had been most effective. All right? Well, my treatments are basically, just so you know, age, so over 45, walkers over 45, supplements over 45, control group. And then the other one would be under 45, walkers under 45, supplements under 45, control group. So basically, in this case, I would have had 6 treatment groups. All right, 6 treatment groups. I guess I should write that down. I'm going to do that on a separate sheet of paper just because I don't have room here, and this will be a mess if I try to. So my treatments: over 45, walkers, supplements, control. All right, so that's 3 treatment groups right there. Over here, under 45, walkers. I keep leaving the L out. Walkers, supplements, control, and that's 3. So I ended up with 6 treatments. Or 6 treatment groups. The last thing that I forgot to do was the response variable. Well, the response variable was BMD, or bone mass density loss. So I wanted to know how much the BMD had changed. All right, so this was my response variable. Okay, I'm going to pause again, let you copy that down because that was quite a lot, although I goofed it up a bit. Sorry about that. All right, so if the findings in part F, and I know it doesn't say part F, are determined to be statistically significant, to what population can we generalize our findings? Well, you can only generalize it to those who are similar to the study. So if the findings were statistically significant, we could generalize the finding to women's age 30 to 60. Why? Those were the ages who were selected randomly, who were in good health. It was not going to apply to those who are in bad health and who are otherwise similar to those in a study. So remember, you can only generalize to the population based on whatever was in your sample. If they'd all been from the state of Texas, then you could generalize it for women age 30 to 60 in the state of Texas who are in reasonably good health. You can only generalize to whatever was in your sample. At the end of the study, it was determined that the women who took supplements and exercise had statistically significant higher BMD level than those who did not. Are the scientists justified in making the claim that exercise and supplements reduce BMD loss? And I meant that either they took supplements or they exercised. And so they can, the scientists can say that exercise and supplement reduces BMD loss for women age 30 to 60. Why? Because this was an experiment and exercise and supplements were the treatments, all right? Because they were the treatments, this was an experiment, we can say that it helps for age 30 to 60. We can't say it helps for 61 up, but we can age from 30 to 60 because those were the treatments. We can say that it actually does help. All right.